BOYD works predominantly on information thermodynamics, both in the classical and now also hopefully then in the quantum regime. And today he'll talk a little bit about some of that work. We will talk on like thermodynamics of predictive and retrodictive complexity. So please, Alan, take it away.
Thank you so much, Simon. I am excited to share this with all of you because, my specialty is primarily classical probability, classical information, classical thermodynamics. But I think that in this specific case, there's some very interesting connections that can be made, and I'm hoping, may inspire you to, explore the quantum thermodynamics of predictive and retrodictive complexity. So I hope I don't make a fool of myself in my discussion of quantum mechanics. If I do, I think it's partially Simon's fault. But I'll start off, with my wheelhouse, which is classical processes in information. And when I think of a process, I'll maybe define it in such a way that it doesn't have to be restricted to a classical system, as I'll define it as a pattern in a time series. So, I did my PhD with Jim Crutchfield, who studied, essentially reconstruction from time series. He's part of this cabal that studied chaos at Santa Cruz. Things like the Lorentz attractor, which has deterministic dynamics, but because of non-linearities in its behavior, it's unpredictable, and it approaches this strange attractor. Now, we want to be able to describe pattern beyond just deterministic systems. Say you might have observations of a Lorentz attractor which are somewhat noisy, which is reflected here. You essentially have a noisy measurement device. Or the Lorentz attractor may have some thermal noise added to its dynamics, meaning that random fluctuations have an influence on the system that carry over to future behavior. And for all these sorts of processes, I'm really talking about like a series of observations, which I often denote with this double arrow. I'm going to bounce around between different notations here. This double arrow means a bi-infinite series from -infinity to infinity of realizations from some alphabet. This is another way that I express it, where the definition of A:B is from YA to B-1. That's just kind of a computer science convention. And with this in mind, what is a pattern? Well, that can really be deconstructed by looking at classical probabilities. So whatever dynamics might exist in your system, and whatever observations you might have of them, you can construct distributions over lengths of these lengths of words that correspond to sequences of symbols, and through analysis of that, you can use classical information, which is minus the sum of p log p. Actually, I know I'm going through a lot of basic stuff here, and please do stop me when I go on too long about something that's maybe not interesting, or if you need more detail on something. Because I have a particular way of viewing things from this perspective. And what we really care about are these quantities that are intrinsic to the pattern, like the entropy rate, which is the entropy of n-length symbols divided by n as you take n to infinity. So this is the irreducible uncertainty that gets generated per time step in your system. So this is sort of a first cut of analyzing these sorts of systems with information theory. But we can say much more with computational mechanics, in which we have this inverse process where we look at statistics and we're trying to reconstruct what could be going on in the black box that's generating the time series. And for this, the core idea is really to capture the temporal correlations in the process. So, if you have, the past, the semi-infinite past of the process and the semi-infinite future, there's some amount of information that's shared between, those two, subsets of the process, and that can be captured by a hidden Markov model. And that essentially means that the hidden states of this Markov model, in this case A, B, and C, capture this shared information. So one way of doing this, which is just algorithmic, if you have the details of your process, is to say, well, given two semi-infinite pasts, we'll say that they're basically the same if they lead to equivalent predictions of the future. So this is just saying that the probability distribution over all future words is the same, given that you observed this past and this past. And if you do that, you define causal states as equivalence classes of these pasts. So the causal state is itself a function of the past. And that allows you to construct this infamous epsilon machine. It's a mealy hidden Markov model in that it transitions between hidden states, and conditioned on that transition yields an output. So in this case, we have A transitioning to B, and through that outputting a 1, A transitioning to B and outputting a 0. And as I said, these are functions of the past. So, diagrammatically, that means that, our causal state sort of contains all of this information, but doesn't contain any information in the future beyond the past. And that's just true by construction, how these past are clustered together. The fact that this is, a function of the pasts. And, yeah, sure.
There is an ordering in past, right?
There is an ordering in the past, right. Yes.
We assume this, but
yeah.
Do you have access to past sequences or no?
You do have access to past sequences if you're doing this epsilon machine reconstruction formally. Yes, you do.
Maybe this question, Tom, what do you need to assume of your process so that this is actually possible to deduce? I mean, some kind of, I don't know, some stationarity or something beyond that?
I mean, stationarity is often assumed to derive the form of a hidden Markov model like this, but you don't need stationarity necessarily. There are non-stationary generalizations of this process where, you still, even if the past isn't semi-infinite, even if it's finite, you can still say, oh, well, I'm going to group pasts up. And that gives you, basically a minimal sufficient statistic of the past about the future, regardless of how long the past is. Yeah.
And what does mealy mean, actually?
Mealy, yes. Mealy is to distinguish it from more. So mealy means that the hidden states produce outputs along transitions, as opposed to more, in which the hidden states are basically a coarse graining, or the outputs are a coarse graining of the hidden states. So it's like this would be a more hidden Markov model if this was 0, and this outputted 0, and this outputted 0, and this outputted 1, right? So it's not Markov in that the redundancy in the labeling means that you can't just know your current state to determine the probabilities of future outputs. Yes, this is edge emitting. This is that's what Mealy means, is edge emitting. Okay, yeah. So the hidden state is sort of a sub-layer of the dynamics that aren't expressed in the process. So in this case, A, B, and C are sort of describing this hidden dynamic over these discrete states that aren't actually observed because all you're observing is zeros and ones. So this process in particular is called the golden mean. The golden mean process, when you're in the recurrent component, produces ones in isolation. So with probability, when you're in B, with probability 1/2, you transition here and output a 1. But you can never follow a 1 with a 1 because with probability 1, I'm saying 1 a lot, you output a 0 from state C. So that is sort of the relationship between the hidden states and the outputs. Okay. So this sort of reconstruction is rather powerful. In fact, there's a recent result with Nicholas Brodeur and Jim Crutchfield that uses this along with some machine learning techniques, reproducing kernel Hilbert spaces to reconstruct the causal states of continuous time, continuous state processes. So I told you that this is the time series that you're learning from in 3 different cases. And this is sort of the causal state projection. And so, in the deterministic case, it's maybe expected that, oh, look, you can recover the causal states exact, or something that looks nearly identical to your Lorentz attractor. And then here with the random noise that's applied to the Lorentz attractor, you find that you've sort of denoised it in recovering the causal states. It's not a perfect reconstruction of the hidden dynamics that are generating the outputs, but it's better than the actual time series itself. And then similarly, when the noise is actually affecting the dynamics, you are recovering essentially those dynamics again. So it's able to sort of recognize when there's sort of extraneous noise in your data, which is one of the most valuable aspects of the process, because say you're flipping a coin, right? What model do you need to flip a coin? If you're going to, one strategy might be to create a deterministic automata that produces the series of coin flips, in which case it's going to be an extremely complex program to reproduce this. But all you really need is a random generator with one causal state that does the same thing at every time step. So from this, we can exactly evaluate the entropy rate. So rather than taking this infinite limit of a very large entropy that, where the dimensionality diverges, you can evaluate the entropy by simply looking at the uncertainty in the output given your causal state, because your causal state is just capturing the past. And you can exactly evaluate the statistical complexity, which is the entropy of the causal states, and it's the minimum information required to predict a process. So this is sort of, I'd say, the first layer of a first layer of computational mechanics. What I want to get into today is, you may see a definition of statistical complexity and think, oh, well, this is the measure. But really, there are a variety of measures of complexity that depend on what operation or how you're trying to generate your process, how you're trying to interact with your process. And where I'm hoping to go with this is showing that it's physically relevant, that each of these complexity measures has an implication. Yeah.
Okay, maybe you're going there, but
yeah.
How difficult is it to compute S0?
S0? Oh, it can be quite difficult. I mean, with the causal state reconstruction, I'd say, this example here, I'd say is one of the examples where it's been most reliable. And I honestly don't quite understand how it works. It's kind of a miracle to me that this works at all. But, sorry, I just whacked my microphone. You do need a lot of statistics to accurately gauge when this equivalence relation holds. That said, it seems to work in some cases, and at least it's a principle by which you can establish when histories should form into causal states.
Because like the second thing, maybe you get there, but like it seems very
Yeah.
kind of near to some corollary complexity measure. Yes, that's why I was asking how high this is to compute.
Yeah.
Maybe you want to get there, so we also discuss this afterwards.
I don't think that's the direction that I'm necessarily going in today, but I'd say it's more computable than the Kolmogorov-ity. It is definitely not computable. Yeah, it is computable if you know exactly your process. Yeah. Okay, so, yeah.
One more question about this example that you showed. This denoising effect, is this something that just comes from finite statistics, or is this something that is like by design there? Because I feel like if the machine was perfect, it should also recreate the noise of the process perfectly, in a sense. Like, I think that it's
Yeah.
more incidental at first look,
Right.
at first sight, than a requirement.
Right. So the reason why I say this is a good mapping for the causal states is because the causal states do not include the noise is like a channel that you're putting on top of this dynamic, right? And this is the dynamic that carries any memory, right? And so the causal states are sort of what should capture the memory of the. So to me, this makes sense, though I should say I don't know all the details of this particular result. I present it mostly because I think it's very impressive, not because I know everything about it. Multiple measures of complexity. Just being totally formal about it, when I'm talking about like information correlations, I'm really talking about, informations, Shannon entropies. So, there is an equivalence between, Venn diagrams of random variables and their information measures. So the mutual information between two random variables, A and B, is, the sum of the marginals minus their mutual or their joint information. And so, we have here that this is this overlap is literally the mutual information between past and future. And this itself is called the excess entropy and is a measure of complexity. It's sort of the minimum amount of information that must be contained by any model that can, produce this process. If your model contains less information than this, it's not producing this process because where are the correlations? They need to be held somewhere, right? For a fair coin, this is 0. Or a sequence of fair coin flips, this is 0. Now, for any generator, as I said before, this was the minimum amount of information. You basically have to contain, the hidden states need to contain this wedge here. And they can do this in a variety of ways. This includes containing information that's totally unrelated to the process. But as I mentioned before, if you restrict to being predictive, meaning that you're a function of the past, this means that you have no shared information with the future. This can be expressed as a conditional mutual information being 0. Basically, the future and the forward time causal states share no information when conditioned on the past. Then, another subclass of generators are retrodictive generators, where you basically flip the role of the past and the future. So any process can be viewed front to back or back to front. So just as you can construct the causal states of the forward process, you can construct the causal states of the reverse process. And you can construct them from each other as well. And so, these are the reverse time causal states, or this is the condition for the reverse time causal states. And then you have corresponding measures of complexity. So the generative complexity is the minimum over all generators of the uncertainty or the Shannon entropy of the generators. The predictive complexity is the minimum over all predictive models of the entropy of the causal states. And the retrodictive complexity has that same definition. The minimum over all retrodictive retrocausal states, the minimum of the entropy of those retrodictive causal states. Now, yeah.
So what is half zero? What is
Half zero?
R0.
R0. R0 is just the generator state. R is to just represent. So the generator is any sort of hidden Markov model. So it's the hidden states of a Markov model that's not necessarily predictive, not necessarily retrodictive. So it's just.
So is it like the stationary distribution of the Markov model of the states? I mean, because
yeah.
It has to be a probability distribution, no?
Yeah.
It's like in the stationary states,
Yeah.
how much each state depends.
Yes, I should be clear. For all of these, usually the distribution is the steady state distribution, assuming sort of a bi-infinite past or a semi-infinite past.
Maybe in the same way, what's the difference between like the S naught plus and the R naught? Like, what's the difference between like the generators and the causal states, basically?
So these are just these are subsets. So each of these is a generator. Every generator is not a predictive generator. Every generator is not a retrodictive generator. So minimizing over the set of all generators means that you have more candidates than either of these minimizations. So they're all basically just mealy hidden Markov models. And it's just that when you consider the space of all generators, the number of candidates is much larger. Does that satisfy? Okay, cool. So recognizing the relative sizes of, the fact that the set of predictive generators is a subset of all generators, et cetera, you can establish this ordering of complexities. You have the excess entropy is less than or equal to than the generative complexity, which is less than equal to both the predictive and retrodictive complexities. And also interestingly, you can have causal irreversibility, meaning that the causal model for the forward process, in this case, would have 3 states. The causal model for the reverse process would have 4. So that means that you have differing complexities in how you try to explain the same data based on how you read it. If you read it front to back, maybe it's really hard to explain. Or maybe an example is like, I have a glass on the table. I push it off the table and it shatters all over the floor. And that's a relatively easy thing to create a causal model for. But you play that video in reverse and you see all these shards of glass start to vibrate and then self-assemble and place itself up on a table. It's the same process, but it's harder to explain in reverse time. It's harder to create a causal model in reverse time for that process. So that was, a sort of breakneck speed review of computational mechanics. And my hope is to tie it to some of the stuff that you're doing here. Specifically, in my analysis and the computational mechanics analysis of classical processes, we have reliable and interpretable measures of complexity, but what about quantum processes? And one of the most interesting, or one of the examples of a quantum process that I think is like very powerful, and Simon and Felix have convinced me of this, is the quantum comb, where you have this sequence of unitary operations, and interspersed you have the ability to do quantum operations that sort of determine your observations. So this has a variety of possible behaviors that I'm honestly unsure about, and I'd like to learn more about. And the interaction affects the observed process, so it seems somewhat different to the way that I know of a process. The way that you as an experimentalist operate with this comb-like device is very important. But I guess a big question is, what are natural measures of complexity in such quantum processes? So in tackling this idea, I think maybe one thing I found helpful to do was restrict the quantum processes to a particular sort of input-output process, where this quantum operation that you do is just sort of exchanging bits. You have an input quantum system, and then it gets translated into an output, and you just leave it there, and take another input quantum bit and put another output and leave it there. And so you're taking a sequence of quantum states and mapping them to another sequence. Now, I just want to make the point that environment here is not going to be, I don't use consistent notation for it or a definition for it. It's somewhat subjective. I mean, like, I'm your environment, you're my environment. Yeah?
Just so I make sure that I understand what you
Yeah.
mean by this quantum state out here. Is that just like the raw quantum state in the processor? Is there a measurement happening there? And you're defining the out thing being what you measure?
I'm so far not assuming any measurement has happened. I think it's nice to sort of leave it as a quantum state, potentially entangled or coherent and whatever. Yeah.
Your choice of input depends on what you get out.
Sorry, can you say that one more time?
Can your choice of inputs depend on the previous outputs?
I believe so, but I'm not sure. I mean, I think there's a parallel that you can make here where you can answer a lot of those questions just by understanding. So actually, let's be concrete here. So your question is, can a past input depend on or a future input depend on a past output?
Yeah.
I see. So far, there's no feedback, I'm assuming, in the system. Yes. Okay. I gotcha. So what you're essentially doing here is just mapping a density matrix over a semi-infinite string of quantum states to another semi-infinite string. And this is sort of like a causally ordered map. Now, to me, this seems very similar to a classical transduction, which doesn't involve a single process, but two processes, an input process and an output process. So the transducer itself has inputs and outputs defined on it, and it has memory states. So a transducer is like a memoryful channel. And the resulting output process is can be expressed as sort of a composition of these two hidden states, sets of hidden states. And in the same way, you're mapping a probability distribution over this semi-infinite sequence to another probability distribution. So it's like a special case of what's happening in that comb that I showed you before. Now, what's happening most precisely in a transducer is that the probability distribution over outputs is defined for any particular input sequence. So, the quantum comb that was shown before wasn't just an abstraction that's like, oh, here's a set of hidden states that maps inputs to outputs. It was a physical system. And in the same way, there's a physical framework for constructing any transducer. And it involves basically the following elements. It involves a work reservoir. It involves some hidden states, X. It involves a thermal reservoir and sort of this interaction region where the states of X can, based on their configuration, can affect the input/output variable. And so the heat bath adds stochasticity, and this allows for any stochastic channel to be implemented from input to output. And so that basically allows for any transducer to be implemented with this set of elements. And so what's happening in essence is, again, not using consistent notation for an environment, the memory states of the channel are receiving an input from its perceived environment, updating its internal state, updating the state of the system, and then writing that state to an output, such that you have this output tape that's growing ever longer, and then repeating the process. And just to make it fully concrete, here we have our inputs, outputs, inputs, outputs, outputs, green is outputs. And we have Hamiltonian control here. So the Hamiltonian control includes the Hamiltonian of the reservoir, the Hamiltonian of the interaction of the memory state and the interaction bit, and an interaction energy between the two. And then these unitaries can be thought of as like the integrated influence of some Hamiltonian as well. And if you see the thermal reservoir and the memory of the daemon as sort of the environment here, then these are the same picture in some sense. You are using the state of the thermal reservoir and the state of the daemon and updating them in this unitary in the same way as you do here. So you could also think of this as like a three input, one for the reservoir, one for the daemon. The state of the thermal reservoir essentially remains fixed while the state of the daemon updates to accommodate the memory of what happened with the input and the output. So, yeah.
Sorry, I didn't quite understand. Like, why does the environment have to be thermal or something? Could you not just have? I mean, I guess there are some processes where maybe thermal environment is not the best thing to simulate that string of data or something. So
it doesn't have to be, but it's useful if it is, because you can show a mechanism for implementing any stochastic channel if you have an ideal thermal reservoir and arbitrary Hamiltonian control over the memory and the input.
okay, but I mean, in quantum physics, you don't need that. You can show physical mechanism in some sense for arbitrary environment by like string dilation or something. So.
Yeah, but I think what you want is a little bit, you want some kind of forgetfulness, like you some kind of entropy that is fundamentally dispersed and cannot, or like some information that's lost and cannot be recovered, which is like, I think what you think.
Yeah. having a large thermal reservoir is useful in that, the way in which it affects the interaction between the memory and the input will be consistent from time step to time step.
Right, so in some sense, this line up here in the quantum curve is actually your daemon or whatever, and there's kind of an almost additional thermal bar there.
Yeah, right, exactly.
Which is dissipating, yeah, okay. Thanks.
Okay, cool. Yeah, good question. Okay, so what about thermodynamics and computational mechanics? And maybe it feels a little bit like I'm taking you on a wild goose chase here, but I promise you there is, a thread that connects all these ideas. The fact is that information has strong implications for what can be done thermodynamically. So, this is a very general picture of how one manipulates a physical system in a thermal environment. You have a work reservoir that changes the energy landscape as a function of time, which then causes the probability distribution over states to evolve as a function of time, and that in itself can therefore cause a computation, or i.e. a stochastic channel from input to output to occur. And these two objects are the probability and the energy determine the change in average energy of the system, which can be broken into two parts. One is the change in energy due to changes in distribution. One is the change in energy, change in average energy due to state-fixed changes in energy. And these can be identified in terms of heat and work. Maybe I have a little, I don't have any internet, so maybe that can wait for another time, sorry. Well, there's a little simulation you can play around with here where you can calculate exactly this work in the process of manipulating sort of a stochastic, a collection of stochastic particles in a bistable potential. And in it, you see that there are strong restrictions on how much energy needs to be invested in order to do different computations. And specifically, whatever you do, you will not be able to violate Landauer's bound that says that the heat that you dissipate into the thermal reservoir must be at least kT times minus the change in entropy of this computing system. So how do we use that? Well, we have our computing system right here. It's the interaction symbol and the daemon's memory. So we can split it up into two localized Hamiltonians. This is sort of the thermodynamic consequences of these sorts of operations come from the fact that they're modular, the fact that the energy landscape here is divorced from the energy landscape of all these other subsystems. And that means that Landauer's bound applies locally over just this computing subsystem. But the global change in entropy includes all of these variables, right? It includes everything that has not yet been computed and everything that has been computed in the past. And it also includes the thermal reservoir. So specifically, the total change in entropy is equal to the heat dumped into the reservoir over the temperature plus Kb times the change in Shannon, minus the change in Shannon entropy. Or sorry, no, this is the change in Shannon entropy of all of these variables. And this is greater than or equal to the local heat that that the local minimum on the heat that's required here. And so you have a combination of marginal entropies here and joint entropies. And it turns out that mutual informations pop out as shown in this expression. Very hard to read. I still can't quite read it comfortably. But basically, you have that any reduction in mutual information between this computing component and all the remaining components corresponds to entropy production, no, minimum entropy production. So, here we have, our information diagram picture where we've got our computing component A, our, remaining bits, our remaining outputs and inputs, and you do some computation, and you know that this, because it's modularly implemented, the information shared between them has to reduce. It can't increase. And the amount that it reduces corresponds to irreversible entropy production. And this is what we call the modularity dissipation. Yeah?
In this type of, let's say, line of questioning or analysis, do you think at all about the relative entropy of this reservoir or stuff like this? I say this because in like sort of quantum thermodynamics, these types of, let's say, equations here, there's like, let's say, a history of them, right? There's this one by Esposito, this one by Wolf, where the relative entropy of the dot is very important.
Yeah.
So I ask because sort of I don't see it here, but maybe you know that it pops up somewhere. I'm curious.
Yeah, so I would say this heat here is the relative entropy, or the minimum relative entropy that's added to the bath. Like this definition of heat is sort of consistent with detailed fluctuation theorems that define the heat as sort of that non-equilibrium addition to free energy. But good question. Yeah, there are sort of ambiguous definitions of heat here and there, but this is consistent. So with this modularity dissipation, we can start to analyze particular types of computations. One computation you could look at, for instance, is what if you have a pattern in your inputs that you want to turn into energy. So that means you're moving thermal energy into work energy. And to do this, you're going to randomize your output as much as possible, make it white noise. It basically means the probability of your outputs is uniform. By contrast, your inputs have some patterns. Say they're the collected works of Harry Potter. And these sorts of processes cannot be expressed as a product of marginals. And if that's the case, then we can basically eliminate the output variables from our expression, and we have a simplified a difference of mutual informations equal to our modularity dissipation. And that allows us to ask the question, okay, of the many ways of erasing this information, you can erase information in a variety of different ways. You could just let it thermalize with the environment, regardless, with no memory states at all, and that turns it to white noise. But maybe you want some memory states. So of the many ways that you could do this, what's the best way of erasing this information? So we have a bunch of candidates for what X could be in relation to the input past and input future. One thing we know is that X is non-anticipatory, meaning it can't know anything about the input future beyond what's predicted from the input past. So that basically means this variable here can't have any overlap with this pure red region. And then you can also show that the thermodynamically best memory, the one which minimizes this to 0, is predictive, because it implies that the information shared between past and future conditioned on X must be 0. So you have this wedge here that sort of characterizes any sort of thermodynamically efficient hidden state for your information ratchet. So, analyzing this, we see that entropy production equals 0 implies that you have a predictive model of your inputs for this sort of computation. And this leads to the principle of requisite complexity. It means that information in memory must exceed the predictive complexity of the environment. So we see that there are physical consequences for the predictive complexity in a transducer. So just to be a little bit more concrete, let's say you have some input process that's structured here. If you had a memoryless transducer, all of the temporal correlations would be dissipated. But if you design your transducer to stay synchronized with these hidden states, then you have 0 dissipation. So we see this result that thermodynamic performance leads to principles of computational mechanics. Yeah?
Quick question. Like, if you have 0 dissipation, isn't that a little bit against like Landauer's spirit in a sense? Like you have an eraser that does not dissipate. I mean, okay, doesn't then, okay, I forgot a little bit what the average sigma is, but like, I mean, it doesn't dissipate heat, I guess, or it doesn't dissipate entropy. Like,
right.
That seems a little bit at least.
Yeah. Sorry, this is an inconsistency in notation. This is total entropy production, which has one term, which is the heat, which is non-zero, and another term, which is the entropy of the environment, which is also non-zero, but they cancel out. Yes. Good question. Sorry, I did not notice that inconsistency. So you can also flip the script and consider creating patterns from energy. So in this case, you're investing work, and in doing so, you're taking uncorrelated inputs, white noise inputs, and mapping them to something structured. And in that case, you remove dependence on the inputs because they're not correlated with anything. And we once again ask the question of the many ways of creating information, which is best? Well, we have our hidden state of the ratchet, of the transducer, and similar to being non-anticipatory, we have the requirement that the memory has to be generative. That is a requirement for creating a process. And so it must contain all this information. And then we apply what's the thermodynamically best model. And it turns out that the thermodynamically best model is that which shares no information with the output past conditioned on output future. So in other words, it's a retrodictive model. It's a function of future trajectories that is most efficient at generating processes. So we have sort of the time reverse of the condition for efficiency when absorbing energy from a pattern. And we have this same parallel. Entropy production equals 0 implies retrodictive, that we have to retrodictively model our outputs. And information in memory must exceed retrodictive complexity of the environment. So there are physical consequences for this other measure of complexity. And we can see this borne out with, say, this parametrized process where z goes from 0.5 to 1, but in all cases produces the same process. It just does it in different ways. Here it's entirely predictive. It's a function of the past, and it dissipates 2/3, and it decreases continuously until it's retrodictive, at which point there's 0 dissipation. So, so we have two causal models for each direction to read a process, and they both have thermodynamic consequences. So, what I've shown to you is, basically a computational mechanics sandwich. I started with computational mechanics, did some hand waving about quantum processes, then started to describe how they're similar to classical transduction, which can be implemented thermodynamically, which we then see leads us back into computational mechanics measures of complexity. So I suppose my observations in exploring this intersection is that even a very restricted subclass of quantum combs has incredible diversity of behavior, because this picture I showed you was a subclass of a quantum comb that was even more general than transducers. And transducers, to me, are a very powerful object. They're Turing complete, in fact, if given enough memory states. So it seems like the quantum combs, or the process tensors, have a lot of that you can do with them. And it implies to me that perhaps one way of extracting quantum measures of complexity may be to investigate what insisting on zero entropy production means about the structure of your quantum comb. So I guess that's my basic sales pitch, is maybe consider what minimum entropy production means when you're looking at quantum combs. Maybe that will take you somewhere interesting, maybe something equivalent to statistical complexity in the quantum realm, maybe something completely different. And so with that, I'd like to thank my various collaborators, my advisor Jim, one of my mentors Dibyendu Mandal, and Amelia Gu, and then Simon Mills and Felix, who have helped me a lot in understanding more about quantum information. So.
Are there any questions?
So you were talking about this entropy production in the causal and retrocausal settings.
Mm-hmm.
Have you thought at all about how these two guys are related, sort of the causal and retrocausal entropy productions? I mentioned this because I bet Felix has mentioned this, that in thermodynamics there's this Tasaki-Crooks relation, right, where you have the forwards entropy production and the backwards entropy production are related in this exponential way, sort of, and you recover the second law of thermodynamics this way. I was wondering if you've run into this in this world.
I've thought about it. I mean, I assume you're talking about essentially detailed fluctuation theorems. Yeah, we have been discussing essentially quantum detailed fluctuation theorems. It's a slightly different picture that I feel is most natural for describing those detailed fluctuation theorems within quantum combs. But I would be interested to think about with transducers, quantum or otherwise, whether there's ways to interpret the sequence probabilities in such an exponential probability way. But I haven't arrived at anything concrete yet.
Because one would hope that you would be able to kind of recover them, and
Yeah.
sort of show that in the general model that you're sort of proposing, you recover all of these well-known thermodynamics ideas. That would be very cool.
It may be. I'd say the one issue with detailed fluctuation theorems is usually the processes that you're dealing with are realizations of the same system, whereas these processes that we're seeing here are, each element is a realization of a different system. Does that make sense? So, the Crookes detailed fluctuation theorem, you're looking at the state trajectory of just a single particle, whereas for this, each of these realizations is a totally separate system. Yeah.
Maybe that's good. Also, is it clear? Like, say I have the ideal process that goes from Harry Potter to white noise, and then I'm thinking about the inverse of that, or the inverse of that, and I want to go from white noise to Harry Potter.
Yeah.
Is it clear if I have one of them, how to I don't know, is it an easy process to go from the forward to the backwards process, or is it like a completely new? I have to start from scratch.
Yeah.
And find the best model again.
This might be where we could use the theorem, because if you insist on the thermodynamically best model, then the forward and the reverse process look exactly the same. But it's when you have non-zero entropy production that if you play the movie in reverse, it stops making sense. So perhaps maybe when you run the reverse protocol for creating Harry Potter that's inefficient, you'll get something other than white noise. And maybe that will be a signature that allows you to say, evaluate how much entropy was produced.
That is essentially what the Tasaki-Crookes thing is.
Oh, okay.
Talking about. It says that the kind of predictive complexity, and we compare that with kind of retrodictive.
Yeah.
Model is exponentially suppressed with respect to how much entropy production is there.
Oh, okay.
Kind of relates these two things in a very nice way.
Okay, that's.
Like Harry Potter to white noise is exponentially easier
Than
than
the other way.
white noise to Harry Potter.
Right.
And
Okay.
exponentially in the amount of entropy.
Exactly.
Gotcha. Okay. Yeah. That seems very plausible. Sorry, I didn't know that was specifically what you were talking about. I thought it was another detailed fluctuation
Yeah,
theory.
there's a little bit.
Yeah. Yeah, I don't always have instant recall, but I should develop that skill. Yeah. Any other questions?
Okay, then let's thank Alex is still here today and tomorrow morning, and he sits in the Europe basement, basically, if anybody wants to have a chat.
Should we press stop here?